Okay. Whoa. Okay. So can you hear me at home? Good job. Awesome. So plan today is to take any questions that folks might have from chapter 16. I will talk about recursion. We haven't sort of done that, and I'll definitely talk about that today. But if there are any other questions before we launch into the recursion stuff, I'd be happy to take those. So has there anything come up from doing the quiz? Questions about map or filter? Any of that stuff? Anything here in the room? No? Sophie, any questions? Anybody at home have any questions? Okay, well then, we're gonna talk about recursion. So I'm gonna actually share my whiteboard for a second and talk a little bit about this sort of in space before we actually get into doing code. So recursion is a very powerful tool that people frequently find confusing. And you may have even run into it without necessarily knowing it by this name or realizing that you had sort of interacted with it. So as an example, you might have actually seen there's this concept in math called factorial, n-bang, n exclamation mark, pronounced n factorial, which is n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. Okay. Now, another way of defining factorial that avoids the ... because ... is kind of weird. There are a lot of issues that come up with ... actually. It's not a very precise idea. We could say that 0 factorial is 1. Now that's kind of an arbitrary choice. It's not obvious that you would choose 1 for 0 factorial. And if it makes you grumpy, you could always start at 1 instead. But it turns out typically we define 0 factorial to be 1. And then we say n factorial is n times n minus 1 factorial for n greater than 0. And that's a perfectly reasonable definition of factorial. And if you think about what does this mean, this is saying, as an example, that 5 factorial is 5 times 4 factorial. Well, what is that? That's 5 times 4 factorial, using this definition again, is 4 times 3 factorial, which is, using that definition again, 3 times 2 factorial, which is 5 times 4 times 3 times 2 times 1 factorial. So 2 factorial is 2 times 2 minus 1, which is 1 factorial, which is 5 times 4 times 3 times 2 times 1 times 0 factorial, because 1 minus 1 is 0. And now, so one concern you might have is this ever going to end? Is Nick just going to type forever and ever, and we will never be allowed to leave? But of course, we get down to here, and now it does end. Okay? Because 0 factorial is not defined in terms of factorial itself. It's just a number. And so we're done. So we can say 5 times 4 times 3 times 2 times 1 times 1. And then that's 5 factorial is 120, if I remember correctly. Somebody could check my math. Okay. And so we're able to define something in terms of itself, but only if we sort of move down as we go. So we're going from 5 to 4 to 3 to 2 to 1, and that there is eventually an end so that we hit the bottom and that stops us from going forever. And if we have both of those properties, that we move sort of in a direction and there's an end in that direction, then this actually works. There's nothing wrong with doing this. It seems a little weird, but it actually works fine as a definition, okay? And this first thing here is called the base case. And the second thing is called the recursive case. Okay. So those are terms I'll use as we go through this. Okay. And there are a lot of function definitions that we can write recursively in a fairly natural way. There are others that aren't as natural recursively. It turns out, and this is, we don't want to get into the weeds on this, but you could either have recursion or for loops. You don't have to have both. That if you have one or the other, you have enough power to do anything by some mathematical definition of power and do anything. And there are formal ways to talk about this. If you major in computer science and you go on, there's a later course called Algorithms and Computability, where some of these ideas are made more precise than I'm going to be able to make them today. But it turns out that you need some kind of construct that lets you repeat something an arbitrary number of times, and a for loop is one way to do that, and recursion is another way to do that. And if you have either one of them, that's enough. Python and pretty much every other programming language give you both, so you can use whichever one you think makes the most sense for the problem you're working on. But you really technically only need one of them. Okay. Now, there's a lot going on here. Are there questions about this before we flip over to Jess and actually write a definition of factorial that uses this? Questions? Any questions at home? Oh, actually, let me make sure I can I hear you? I think I have the volume up this time, so I think I ought to be able to hear you if you make it sound. Any questions at home? Going. Okay, let's go to Jess. Let's type something in. So let's see, I'm gonna need to share my Jess. So let's actually define factorial. So 0 factorial, I'm just putting this in the comments. So we can say def factorial of n. If n is 0, we'll just return 1. Otherwise, and we'll assume here that n is at least 0. That didn't work. So if n is at least 0 and it's not equal to 0, then it's bigger than 0. So we can return n times factorial n minus 1. And that should work. Save. CSci 1, 2020, 11, 18.py. Load. Factorial of 5 is 120. Factorial of 6 is 720. Factorial of 10. And factorial grows pretty quickly. So you get very large numbers pretty fast. That number goes on and on and on and on. Okay. And if we use the watcher, we can actually see, let me add the variable n, list of things we want to keep track of. If we use the watcher, we can see that it started, this is fairly small text, but it started at 10, then it did factorial of 9, and then factorial of 8, and yada, 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 yada. And then eventually we got down to def factorial of n, or of 0, and it said if n is 0, that would be true, and we would return 1, and that ends things, and it can do all the multiplication back up the chain and get 3,628,800 as the answer. Okay. Questions? About that? Going? Any questions at home? Okay. So let's see, I want to get rid of the watcher. Now, we can also do recursion. So this is recursion on numbers. We can also do recursion on things like lists and strings. If we, let me flip back over to my whiteboard. And I'm going to make a new board. So with numbers, on natural numbers, we usually work down from n to 0. Okay. Typically subtracting 1 at each step. Now, that's not the only way to do it, but that is a common pattern. And we saw that with the factorial. We started with n, we subtracted 1 every time, and we worked our way down to 0. We can get a similar thing to happen with something like a list. You can use the empty list to play the role of 0. And remove the first item, let's say remove the first item as something like subtracting 1. And this allows us from big lists, or allows us to recurse on lists, let's say. So as an example, let's imagine that we want to write length. We haven't needed to write length because length was built in. Okay. But let's say we want to write a function length. So we want mylen to compute the length of a list, array, whatever you want to call them. Well, let's start with this, the base case. What's the length of the empty list? This is an easy question. How many items does an empty list have in it? None, 0, right? So the length of the empty list is 0. Notice that this is very similar to 0 factorial, right? We're defining the base case here. We're saying what's true at the bottom. But for a list, the bottom is the empty list, not 0. Okay? But we're going to get down to the empty list however we do it. Okay? And so this gives us the base case. This is the bottom of the process. Okay. There we go. Now, if we have a list that's not empty, that means it has a first thing and it has an everything else. Okay. And so we can say it's one more than mylen of the everything else in this case. So we could say XS1 colon. So I'm using the slice stuff that we did earlier. And I can say 1 colon as a way of giving me everything but the first element of the list. Because the first element's at position 0. And so position 1 is the second element. And so 1 colon is everything but the first element. And so that'll give me the rest of the list. And this recursive definition says that the length of the whole list is 1 more than the length of the rest of the list. Okay? And because this is shorter, the rest of the list here is shorter than the original list, we are moving toward the base case, the empty list. We'll take one item out over and over again, and we'll eventually get to the empty list, at which point we'll be able to return 0. So again, this won't go on forever and ever and ever. Okay? This is pretty weird to think about. You should totally feel free to shout or ask questions or just, you know, whimper quietly and I'll repeat things, whatever's working for you. Questions about this before we try this out in Jess? I feel like Joseph's got a question. No? Okay. Let's go back to Jess. We'll type that up and see if that works. So mylen of the empty list is 0. Mylen of the list XS is 1 plus mylen XS the rest of the list. Then we'll define it. If X's is the empty list, return 0. Else, return 1 plus mylen XS 1 colon, you know, boom, bop, bibbity, babbity, boo. Program mylen 5896320 is 7, which is correct. Correct. And if we turn the watcher on again, And let's remove n and add xs. And then if we just run this guy again, so we can see that xs1 colon removes the first item from the list. We had 589, then we had 89, then we had 9, right? And so we removed the first item each time. We eventually got down to mylen of the empty list, and it said, hey, the empty list is empty, so it returns 0. And we were done. Okay. Questions? Now, if you're feeling a little anxious at this point, on the quiz, there is only one problem that uses recursion, and it basically gives you the recursive definition. All you have to do is convert it to Python. So you're not having to do anything too terribly complicated. There will not be anything profound on the exam about this. I mean, there'll be something small, but it won't be anything like bigger than, say, what's on the quiz, right? I'm going to do some more complicated examples, but you're not going to be expected to like write some super complicated thing on the final using recursion. But it's an important concept, and I do want to talk about it. So, questions? We covered a lot, so feel free to ask. So I'm going to do one more example that's a little less obvious, but which I think is interesting. So let's consider, I'm going to go back to my whiteboard. Let's consider this question. So imagine we've been asked, write a function triangle that prints a right pointing, and I'll provide an example, triangle with n. So what do I mean by this? As an example, triangle 5 would print so that's a triangle, it points to the right, and its width is 5 asterisks. Okay. And that if I give it 3, I get a smaller triangle. If I give it 10, I would get a much bigger triangle, right? And notice that the number of rows is also a function of n, right? If each row is going to be one bigger than the row before it, then we need n rows to get from 1 to n, a row of length n. So we're going to get, it's going to be not only wider with bigger n's, it's going to be taller with bigger n, right? Does that make sense? So the question is, how might we do this? We could totally do this with for loops, but we'd have to do some math. And we'd have to work out the coming down again on the other end. So it'd be like getting bigger and getting smaller part. So we could totally do it that way, but it would be, it would take some futzing. We could, however, as an alternative, do it with recursion. So we might notice, for example, that triangle 3 is that, and triangle 4 is that. And the important part here, let me get a drawing tool. Oh, stop. Let me draw. There we go. That the important thing to note here is that that's triangle 3. So triangle 4 is triangle 3 with sort of another row of asterisks in front of it. Does that make sense? And triangle 5 is triangle 4 with another row of asterisks in front of it. And triangle 3 is in fact triangle, oops, undo. Be a little more precise here. Triangle 3 is triangle 2 with another row of asterisks in front of it. And in fact, if we want to get really excited, triangle 2 is triangle 1 with a row of asterisks in front of it. So there is, in this example, and it's not obvious, like I wouldn't necessarily expect people to look at this problem and go, well, that's clearly a recursion problem, right? But there is actually a fairly natural sense of recursion here that we can use. That we can think about triangle 4 as being built out of the result of calling triangle 3. Like if somebody gave us triangle 3, we could make triangle 4. And somebody gave us triangle 4, we could make triangle 5. Okay? And in particular, what I'm going to do here is I'm going to keep track of all of this as a list of strings. So I'm going to say triangle 3 is a list with this string, comma, this string, comma, this string, comma, this string, comma, this string, and then a closed square brace. Because then to go from here to here, I just need to append one more asterisk to every one of these, and then stick in a single asterisk at the beginning and the end. At some point, I'll have to print those strings out. We can do, that's easy enough to do. But if we keep it as a list of strings, it'll be easier to do the recursion, because the recursion just is tack another asterisk on everybody in your list, put a single asterisk at the front of the list and a single asterisk at the back of the list, and you're good. Okay. Questions about that before we try to make it happen? Anybody? Questions at home? Doing okay? Or are we just baffled beyond all understanding? No idea. Complete silence. Okay. Well, then I'm going to press on. So let's go to Jess and let's see if we can make this thing happen. Stop sharing. Share screen, Jess. Okay, so I'm going to start out by writing a function make triangle that takes n and returns the list of strings needed to make the triangle. So then this will be the recursive function, and then triangle will actually just call this and then print the results. And I didn't spell triangle correctly. That's important. So if n is 0, Well, if n is 0, a triangle with width 0 is essentially an empty list. You just don't have any rows or any columns. Okay. Now, triangle, n minus 1, boom. So small triangle is what we get by calling make triangle on the smaller number. Okay. So this might be, for example, well, this is awkward. You know, let me just share my whole screen and I can probably hop back and forth a little. Oh, no, I can't actually because it's whiteboard. So if small triangle is like 4, now we want to make the whole thing, and we do that again by adding 1 asterisk to the front of everybody in 4, and then tacking a string with just 1 triangle on the front and the back. Now, if we need to add 1 triangle to everything in this row, or every string in this list, what is something we talked about Monday that does something to every item in a list? What? We could totally do a for loop. But on Monday, we talked about a functional programming tool that we can use to do something to every item in a list. Map. So we could use map to add an asterisk to the front of every string in the list and get back a new list. Very fancy. Sneaky that I actually am using the stuff we did Monday, isn't it? So let's actually try that. And I could do this with the lambda. But instead, I'll actually go ahead and make a new function. So add asterisk takes a string and returns a new string that is the asterisk plus the old string. So it adds 1 asterisk to that string. So here we want to return that plus, well, okay, yeah, let's break this up a little bit. I was going to do it all kind of in one line, but with asterisk, say map, add asterisk on small triangle. That should give us everything from the small triangle with 1 more asterisk in it. Oops, what happened there? I don't know. And then we'll return there we go. I don't really like that name. So recursive call gives us the smaller triangle. Then we add 1 more asterisk to each of those strings. And then here we add a single asterisk to the front and back. So let's see if this makes any sense. Save, load, make triangle. We still don't have the printing part worked out, but we'll see what we get there in a second. So we have 1, 2, 3, 3, 2, 1. So we have 2 copies of 3 here. That doesn't seem good. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. The problem is actually starting at 0 here. I really wanted to be able to start at 0. But if we do this, then we get, when we go to make triangle 1, so if we do 0, we get this. Make triangle 1 really should have just been a single string with 1 star in it, but we get this and this with the empty list in between. So I probably need to actually have my base case be 1 here. This is one of these things where sometimes you kind of, typically 0 is your base case, but it isn't always, and that's life. Have 1 string with 1 asterisk. So in this case, oops. Now that gives us the right thing there. And we get 1, 2, 3, 4, 3, 2, 1. So we've got the right strings here. And now it's just a matter of printing them. And this works for arbitrarily large things, like that goes up to 10 and then back down to 1. I'm not going to count the number of asterisks, but we'll assume that it's probably true. So then if we def triangle and make, let's see, strings is make triangle, and here we could just say, could we do this? I think this will work, but I'm not sure because I'm not sure print's a function. This might not work. We'll see what happens. Yeah, no, print's not a function, so we can't actually do that. That's too bad. So we'll do a for loop. Easier. For s in strings, print s. Boom. Load. Order. Triangle. Can't spell. 5. Let's make this taller. Woohoo! We need a triangle up with 5 things. A triangle with 10 things. Triangle with lots and lots of things, but I won't. And so the recursion here allows us to avoid doing a lot of the math that we'd have to do if we did this with for loops. In particular, the going back down math would be kind of a nuisance. The going up math wouldn't really be a problem because, you know, I would be 1 and then I would be 2 and I would be 3 and you would just print that many asterisks. But then somewhere in the middle, you have to be like, oh, we reached the middle, so now we want to print I minus something asterisks, or no, something minus I asterisk. To get the smaller things. You'd have to kind of work out what the edge cases were. Whereas here, we didn't have to do that. We just always stuck an asterisk on the front of every string, and tacked single strings on. We did have to do a little fiddly bit here with figuring out what the right base case was. So I got that part wrong initially, but that was not hard. And it didn't require like thinking. You just had to be like, oh, well, it doesn't work with 0. We'll start with 1. So that actually works very nicely. Now that was pretty complicated. We did a lot there. Are there questions? Here in the room? Are there questions at home? Does this make any sense at all? Some people nodded here. I'll call that a win. So, grab my book. There's one other place where recursion is really important and arguably hard to replace with loops. Not impossible, because as I say, if you've got one, it'll let you do everything for the other that the other does, but it's a lot more complicated. Like there are places where there's sort of a naturally recursive way of thinking about things. And a common example of that is in directory trees, folder structures on your hard drive. So let's imagine that we've got, oh, come here, you know, a top level folder users. And in it, we've got, so maybe we've got fee, and maybe we've got, oh, no, I didn't want to do that. Come here. Smith. Oh, stop it. Okay, and we've got others, but I'm just going to pick those two for now. And then McPhee has a whole bunch of folders in the McPhee folder. So maybe there's CSci 1201 as a folder, okay? And maybe there's CSci 3403 as a folder, okay? Because I'm teaching several different classes at the moment. And then, you know, maybe CSci 1201's got folders inside of it, and CSci 3403's got folders inside of it, right? So you've got folders that have folders that have folders that have folders, but they also have files, right? So 1201 might have a bunch of files as well as other folders. So, you know, it might have CSci, oh no. Yeah, I think it was, I'm doing CSci 1201, 2020, 11, 18.py, okay, as a file. So that's a file, doesn't have anything, it's not a folder, it doesn't contain other files, it just is itself, okay? Now, this is, so does this setup make sense? This should all be familiar. You've all used folder structures like this. You may not have thought about them very hard, but you've used them. This is an inherently recursive data structure, an inherently recursive way of storing data, because a folder contains either files or other folders, okay? So how do we define a folder? A folder is defined in terms of other folders, okay? And a folder, McPhee, contains files and other folders like CSci 1201 and CSci 3403. the folder CSci 1201 contains files like this Python file and possibly other folders. Maybe I've got a folder for every assignment, as an example. Okay? And so if I want to count the total number of files in a folder, for example, I'm probably what a natural way to deal with that would be recursion. That if I have a single file, then great, that counts for one. If I have a folder, I do a recursive call on the folder to say, hey, count all the stuff inside of that folder, and it's going to go through and say, that's a file, counts for one, that's a file, counts for two, that's a folder, we'll recurse into that and open it up. And there's an example of this in the book. So they talk about this in, where is it? Yeah, okay, so in 16.4.1, they talk about recursive directory structures or directory traversals. And they've got an example, which we'll do here, of printing all the files in a directory. And that's an inherently recursive action because you're going to want to, if it's a file, you print it. If it's a directory, you call print all files on that subdirectory. Okay? And then the print all files on McPhee is going to say, is this a file? If it is, print it. If it's not, call print all files on CSci 1201. And that's going to say, is this a file? If it is, print it. If it's a directory, call print all files on that directory. And that gives us a very natural way to process something like this. And it's really easy because directories contain directories. Having a function like print all files be able to call print all files makes it much easier to talk about things that contain themselves or things of the same type. Okay? So we're going to walk through that example here in a second. But are there questions about the structure before we go to Jess and actually look at code? Okay. Let's stop sharing this and share Jess instead. Okay. So we're going to def print all files. So this should print the names of all the files in a directory, including its sub, etc. directories. So, okay. Does that make sense? Now, this is going to use some Python, and this is all, I should make it clear in case it's not obvious. All this recursion stuff is just Python. There's nothing just specific about it. This is available in any version of Python. And in fact, basically any programming language since, before you were born, supports recursion in some way or another. So recursion is a pretty widely used thing. It's not specific to Jess or media or this class. It's just like, hey, it's a thing. It's an important programming concept. So one question you might ask is, well, how do we find out what files are in a directory? Turns out that there is a tool to do exactly that. So os.listdir is a tool that lets us list the contents of a directory. And OS here is a thing we have to import. We haven't really done anything with imports. But in Python, you can have libraries that you want to bring in and use to solve particular kinds of problems. And there are actually very large, powerful libraries in Python that provide a whole lot of tools for doing all kinds of different things. Jess sort of preloads a bunch of libraries for media stuff, so we haven't had to say import. If you were doing this in a more pure Python environment, you'd probably be importing a bunch of media tools. But Jess sort of cooks that stuff in so that as beginners, you don't have to think about that stuff. And I don't have to explain it to you back in August when everything was so confusing at the beginning anyway. But here, it's like, yeah, you probably ought to know that there are these libraries. And OS stands for operating system. And it gives you tools that let you interact with like the file structure on the operating system. So if we import OS, then we can say things like os.list_dir. So again, noun, verb. The noun is the operating system, and the verb is list the directories, the contents of the directory. And it takes a directory and it gives us back a list of files. Okay. And now we can loop over those. And we can say that the full name is the name of the directory plus the name of the file with a slash between them. So we're building the name of the full path to the file. The file would just be like paper.txt. But if we're listing the contents of the directory homework, then we want this to be homework / paper.txt to distinguish it from some other file called txt in some other folder. Okay. So this builds that out. Then now we have to decide if this is a directory or not. Because if it's a directory, we want to call print all files on it. And if it's not, we just want to print the name. So we're going to need to ask the question, if is directory full name. And we're going to define that in a second. That actually doesn't exist, although it very nearly exists. But we're going to write a little function that does that. So if it's a directory, then we'll call print all files full name. If it's not, then we'll just print full name. So here's the recursion part. If it's a directory, then we'll call print all files again, right? With full name saying, hey, we found another directory. Go through it. And if it has a directory, this will happen again. And if that has a directory, this will happen again. And we'll just walk our way down through the tree, opening up every directory as we go, until at some point we get something that is not a directory. And when it's not a directory, we just print its name. Okay? It's a lot. Questions? It will start with whatever directory we give it. And we could give it the very top. So I forgot to repeat the question. So Zeke's question was, does it start at the top, the most broad directory, and go down? It starts with actually whatever directory we hand it. So if we handed it the very top of the file system, yes, it would then print everything, and we would be here for a very long time. If we started at, say, my home directory on this computer, there's not that much there. There's still going to be a fair bit, but it won't be like enormous. If we start with my desktop directory, there'll be less. If we start with my CSci 1201 directory on this computer, there'll be less still, okay? So it depends on when we call it, we'll hand it something. So actually what I'm going to do is call pick a directory to get a directory or pick a folder to get a directory, and I'll hand that to this, and then this will go from there. Does that make sense? Good question. Other questions? Okay. So now we need to define is directory. And we're going to use another library. Oh, I overcapitalized there a little bit. We're going to use another library called file. So I'm going to have to import java.io.file as file. And this is, you can just take this as magic sauce, but we're basically importing this file thing that allows us to ask questions about files. And so here we're saying construct a file object out of this name, which as a consequence, so this checks that the file exists and what kind of thing it is, what permissions we have on it. It actually does quite a lot of stuff. All we care about is from the file status, one of the pieces of information that this returns is whether or not that thing is a directory. So when it creates a file out of file name, the status that it returns includes knowledge about whether that thing is a directory or not. So we can basically turn the file name into a file, get the status, and extract from the status whether or not it's a directory. And there's no reason why you would have known any of that. Like that's all stuff you would find by looking at the documentation for the relevant libraries. But this will now work in theory, and we'll find out. But this ought to actually, let's see, if we say folder is pick a folder. I said what would be least troublesome. Let's actually do my 1201 folder. This is going to be actually fairly long because it's got the whole media set of files, but whatever, we'll see some stuff happen. Print all files. So in theory, this should start to spew out tons of names of files, and it'll scroll by pretty fast, but it ought to work. There we go. So we got, I'm not going to scroll through all of it, but we've got things that were pictures that I made. We've got the folder media sources and all of its contents. Okay, so it did go down inside a subfolder, media sources, and get its contents. It went down inside a subfolder. So there's a music sounds inside media sources that has music sounds in it. It went down inside that and printed those names out. Blah, 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 blah. Right? So this did, with a fairly small bit of code and a little bit of operating system magic, print all the files in a folder. Okay. And so it's using recursion. If the current name is a folder, a directory, then we will recursively call print all files to handle its contents. And if it's not, then we will just print the file name. And that recursion on the inherently recursive directory structure does really nice things. That's very cool for us. So Questions? That was a lot. Feel free to be stunned. Questions here, questions at home? Anybody? Going. So we got 4 minutes. Let's do one other directory example. This prints all the files. That's actually pretty useful. Let's also, or as a second thing, let's write something that counts all the files. How many files are there? Could be a useful piece of information. You might also want things like how many JPEG files are there, or how many WAV files are there, right? There's a lot of things like that we could do, and that we could do all of those with this sort of form. So let's actually try counting files. So def count all files. So here again, we need to get the list of files in the directory. Now, that's a list. We could say that, but that's not going to quite work. So what's wrong with just returning the length of that list? What are we going to miss out if we do that? Correct. So Zeke said that's not counting files that are in folders in that list. So if files has a directory inside of it, this just counts that directory for one and ends. It doesn't look inside of that and say, hey, what else is in here? Are there other things that I care about? So that's not going to work. That would work if we just cared about the number of top level files and folders. But it doesn't sort of dig down recursively and get all the goodies, okay? So we probably want something like num files is 0 for file in files. Again, full name equals directory file. And if it's a directory, then we want num files to be num files plus count all files in that directory. So we want to recursively count everything from here down and then add that to our total. Otherwise, we just want to add 1 because it's just a plain directory. And that gave us 660 files, most of which are probably in the media folder that came with the book, because there are all those pictures and WAV files in there. But that works. We can recursively count the number of files in a subfolder and then add that into our total, and life is good. And time ran out, so I should be quiet. Are there questions about anything in the 0 minutes that remain? that would be all that all the time I was going to spend on chapter 16, unless there are questions. If there are questions on Friday, we can totally talk about that. Otherwise, Friday we'll talk about chapter 17. So we'll start making that happen. Questions? Going. Okay. Everybody go have a good day. And I will see you online Friday.